Greetings, calculus fans. Um, we will review problem 110 on page 146 today. This is from section 2.2, and this is a common question, and it is one that students sometimes fail to address appropriately with the proper mathematical notation and the required information. So let's take a look at it, and let's see what we're looking for. We're finding a and b such that f of x is differentiable everywhere. Okay, so the partition takes place here at, let's see, at 2, x equals 2. That's where the definition switches from f of x equals ax cubed to f of x equals x squared plus b. In order to show that a function is differentiable, please remember that first we need to address continuity at that point. Now, to establish continuity, we need to find the value of f at 2. And so we end up with, let's see, 8 times 2 cubed. So that gives you 8a. This needs to be on your paper. That way it shows thorough analysis on your part, along with finding the limit as x approaches 2 from the left, which of course would involve f of x equals ax cubed. And so very quickly we end up with 8a. And then of course the limit as x approaches 2 from the right. Okay, these are the three conditions that we must check for. And of course we must get the same y value for all. And actually I meant to put limit as x approaches 2 from the right for x squared plus b. What I had earlier, the f of x as the argument there, that's fine, but I think this is more illuminating, so I strongly encourage you to record this expression as I have indicated here. And so what do we get? We get 4 plus b. Okay, now in order for the function f of x to be continuous at x equals 2, the 8a must equal the 4 plus b. Now this is basically a linear equation in terms of a and b, and it reminds us a little bit of algebra 1. That's fine. Now we must continue and of course also find the derivative. Okay, in other words, 8a must equal 4 plus b. Okay, and also we have, let's see, f prime of x is equal to, we have, let's see, 3 times ax squared, and we have 2 times x. B is a constant, so it's gone. And remember, we don't know whether the derivative exists at 2 or not, so we're going to simply explore before we make a conclusion. Consequently, this is x is less than 2 and x is greater than 2, okay? And let's find the limit as x approaches 2 from the left, and we discover that that is going to be, of course, the limit of 3ax squared. And so what do we get? We end up with, let's see, 4 times 3a, so 12a. Okay, we also need to find the limit as x approaches 2 from the right, which would involve 2x. And so let's see, we end up with, let's see, 4. Now, in order for the function f of x to be differentiable at x equals 2, we need to have 4 equal 12a. So the left-hand limit and the right-hand limit as x approaches 2 for this f prime must be the same. So we can simplify this, and of course we end up with a being 1/3. And once we have that, then we can come back to this problem here. And so this is a system of linear equations. We plug in here and we have 8/3 is equal to 4 plus b. And of course, 4 is the same thing as 12/3. So we subtract 12/3 from 4/3. And we should end up with, if we do this correctly, a negative 4/3 as the value of b. Okay, so we've checked for the conditions, the items that I need to have in my work, 1, 2, 3, and I must set that so that the 8a is equal to 4 plus b, because that is a necessary condition of our theorems for continuity. And then, of course, for the derivative to exist, then what we need to do is to make sure that the right-hand limit for this derivative is equal to the left-hand limit, and I think this was the left-hand limit. Now this is the right-hand limit. Just stating that is not sufficient. We must use the mathematical notation that I have used here, and then we apply techniques of Algebra 1 to discover that indeed the necessary conditions for continuity and differentiability exist when the b value is -4/3 and the a value is 1/3. So this concludes our exploration of this problem. But again, we touched on a lot of the important, notational requirements and communication requirements that you are expected to do in order to earn credit for these problems. Okay, thank you very much. Until next time.